Okay, let's get started. Same thing as before, 20 questions for us to go through. These are from, I think, 2021. I don't know, 2021, 22, or 22, 23, something like that. Anyways, this is from year 2022, 20 short poems, intermediate class and division, same as last time. We're just gonna go through them one by one. Number one, let's get right into it. Number one, Boolean algebra, simplify the following Boolean expression, right? A lot of the Morgan's law, a lot of parentheses. So let's start by splitting that up. First, we can use the Morgan's law to um, break up the not bar at the or symbol right there. So that'll give us not over AB, and then this long not bar over B plus C with an A over here. We can break this up. You can break it. Sorry, ow. We can break that up and we can also break it up here at the two and operators, I guess. They're not really seen between the A, B, and then the between the B plus C and A. This extended not bar over AB becomes not A plus not B. And then on the right hand side, right, we have a double not bar over the B plus C, but because they're over the exact same thing, they're just going to cancel each other out. So this becomes B plus C just on its own plus A, right? And I'm actually going to get rid of this parentheses and move it to the outside because they're all pretty much the same thing. And then we can kind of just FOIL multiply it out. So we have not A times B plus not A times C. Oh, no, that's right. Not A times A just gives us zero, so that cancels out. Not B times B also gives us zero, cancels out. Then we have not B, C, and then A, not B. Oh, wait. No, I lied. Sorry, I didn't see that I missed the not by there. My bad. Okay, never mind. Sorry, we need to refoil this. That makes a bit more sense. Okay, anyways, we have not A times B plus not A times C plus not A times not A just gives us one regular not A, right? The same thing as saying like 0 times 0 or like 1 times 1. Not B times B cancels each other out. Not B times C becomes not BC. And then we have not A, not B, right? So after we finish getting rid of all the parentheses, we finish multiplying out. This is what we're left with. But because we have a not A here by itself, this can cancel out a lot of other things. So it gets rid of this, it gets rid of this, and it gets rid of the third one as well. And our final simplified expression is going to be not A plus not B times C. The answer to this is going to be B. Okay, number two, how many ordered pairs make the following Boolean expression true? Let's get rid of this or operator and the extended not bar. So actually, let's do this first, right? This extended not bar using the Morgan law going to simplify to not A plus not B. And then we have that plus B here. Now, this is a property. When we have a not version of something being or to another version of it, right? What is this always going to simplify to? This is always going to simplify to just one. Why? It doesn't matter what the value of B is, whether it's 0 or 1. If you have one and then like the not version of the other, we're guaranteeing that one of them is going to be 0 and one of them is going to be 1. And therefore, if we or the two of them, right? We're always going to end up with 1. It's a very similar property as to when you like it's also the reason why when you multiply a not version of something to itself, when you multiply, not add, right? It cancels out and becomes 0 because 0 and 1 is going to give you 0. Likewise, now that we have a not A plus 1, it doesn't even matter what the A exactly is because anything or together with 1 is going to give us 1. So basically, this entire thing on the right-hand side, we can disregard it completely as a whole, right? This entire thing just simplifies to 1. So no matter, what we get from here, if we get like a true value here, that's the entire thing is going to be true. If we get a false value here, it's going to be false. We do not need to care about this at all. So that also tells us we don't actually need to simplify this out. This is an XOR operator. There's a total of 4 different ordered pairs that we need to look at, right? A the order pairs are when A is 0, B is 0, when A is 0, B is 1, when B is 1, when A is 1, B is 0, and then when both of them are 1, right? That's just how the order pairs work. And we know that for an XOR operator, it's going to return true in 2 out of those 4 ordered pairs when A and B are 0 and 1 or 1 or 0 respectively. So I don't even need to like simplify that out. I know immediately that the answer to this is going to be C2, right? That one actually required a little bit more thinking. Obviously, if you did solve out, it like wouldn't have made a difference, I guess. You would still end up with the right answer, but to make your life a little bit easier. All right, number 3, bit string flicking. Evaluate the following expression. This is just parentheses within parentheses, so we're just gonna work from the inside out. Um, this is a bit string made up of 1, 2, 3, 4, 5, 6, 7, 8 digits, right? Which seems to be a problem when we take a deeper look at these operators, right? We have something like well, the other ones are whatever, but LSTAR 12 is kind of where it's a little concerning, right? How are we supposed to circle like the leftmost 12 digits and then circle them over when there's only 8? Well, you have to remember that for any circ operator, anytime you have whatever number of digits there are, uh, it's essentially going to be like a repeat of itself after every single multiple of however many digits you have, right? So in this case, LCirc 8 is the same thing as just coming back to this 12, original 12-bit string. Then that also means if we just take LCirc 8 and we circle and move the leftmost 4 digits, like an additional 4 to the right hand side, that's going to give us the exact same thing as LCirc 12, right? So in short, anytime you guys see a number that is bigger than the number of digits that you do have, all you have to do is basically find like the modulus of it. So in this case, 12 modulus 8 is going to give you 4. I was gonna say subtract, but sometimes it'll give you something really like ridiculous, like let's say like 100, right? Basically every 8 like circles, it's just going to reset. So if we wanted to figure out what the denominator is or however many we're actually shifting it by, we can just do a modulus. So in the case of LSARC 100, it'll give us like, I don't know, 4. Oh, that's also 4. Well, yeah, so there you go. There's that one. And then it's a similar idea for L shift, right? But the only difference is for shift, it kind of just gets rid of however many digits on whatever side and then replaces the empty spaces with zeros. So if you ever see a left or a right shift with a number that is greater than the total of number of bits that you guys do have, it's just going to be an empty, not an empty bit string, but that bit string is just going to be composed of all zeros, right? Anyways, I'm yapping a little too much. LSARC 4, we take the leftmost 4 digits and we move it to the other side. This gives us 0, 1, 1, 0. 1, 0, 1, 1. And L shift one of this, we get rid of the leftmost one and we add a 0 to the right. I'll rewrite it. Give us 1, 1, 0, 1, 0, 1, 1, 0. RCirc 6, we take the 6 rightmost and we move it to the left. That gives us 0, 1, 0, 1, 1, 0, 1, 1. A not operator is going to revert every 0 to a 1 and every 1 to a 0. So this gives us 1, 0, 1, 0, 0, 1, 0, 0. Finally, R shift 2, we get rid of the rightmost 2 and add 2 zeros to the left. So we're left with 0, 0, 1, 0, 1, 0, 0. That is going to be answer choice. None of them. What the heck? Where did I mess up? 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0. Wait, what? 0, 0, 1, 0, 1, 0, 0, 1. Oh wait, no, I didn't mess up. What am I saying? Oh, jeez, Chris, I'm actually losing it. Sorry, the answer to is C. I don't know why I didn't. I'm not sure why I didn't. Bruh. I'm not sure why I didn't even see that. Anyways, number 3, the answer is C. Okay, my bad. I'm a little puzzled. Number 4, another bit string flicking problem. How many different values of X, a bit string of 5 bits, makes the following expression true? The entire left-hand side we can just simplify and solve as is. The right-hand side, x is going to be set at equal to lowercase a, b, c, d, e, but let's just leave that as is for now. Let's solve the right-hand side first. So before we can do any of the ors or the not, before we can do the or and the and or whatever, we have to solve these unary shifts and circs and not first, right? So our shift of 0, 0, 1, 1, 1 is going to give us 0, 0, 0, 1, 1, right? We get rid of one digit on the right and then we add a 0 to the left. L circ 2 of this, we take the leftmost 2, circle it to the right, we get 1, 1, 0, 0, 1. And then finally, the not operator, we just flip everything. So 0, 1, 0, 1, 0. Now, between an and an or, remember the acronym is NACSO, so we do and before or. And of these two binary bit strings give us, what does that give us? 0, 1, 0, 0, 0. And then when we combine that with the or on the left here, we're left with a 5-bit string looking like 0, 1, 0, 1, 1. So this is going to be our entire left-hand side. Now, as for our right-hand side, we have, again, x is equal to lowercase a, b, c, d, and e. A, B, C, D, and E. R circ 2, we take the D, E and move it to the left. So we have D, E, A, B, C. And then in L circ 1 of this takes the D and then moves it back to the right. So now we have E, A, B, C, and D. This is going to be set equal to 0, 1, 0, 1, 1. The question asks, how many different values of x make the following equation true? Remember, when you guys are solving for this, the equation for how many different values of x makes anything true, right? It's going to be like 2 to the power of however many asterisks you have. Now, in this case, we don't have any asterisks. The number of asterisks is 0. A, B, C, D, and E each have to be a very specific number, whether it be 0 or 1, for our value of x to return true, right? A has to be 1, B has to be 0, C has to be 1, D has to be 1, and E also has to be 0. In which case, there is only one value of an x that makes the equation true, and therefore the answer is none of the above. Moving on to number 5, recursive function. Find f of 17 if given blah, 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 blah. There is nothing special or fancy or new about this, right? It's just more recursive function. So f of 17 is equal to x of 17 that goes in our first branch. We have f of 2 times f of 14 plus 1. F of 14 is equal to 2 times f of 11 plus 1. F of 11 is going to be equal to where does that go? In our second branch. This is another greatest integer function. So 11 divided by 2 is 5.5. We just truncate that. We just round down, make it f of 5. And that is subtracted by 3. F of 5, again, 5 divided by 2 is 2.5. Truncate that, gives us f of 2. F of 2 becomes f of 1. That one divides nicely, divided by, minus 3. And finally, f of 1 is equal to 1 minus 4, which simplifies to negative 3. And then once we have our negative 3, we can make our way up. So f of 2 is going to be equal to negative 6. F of 5 is negative 9. F of 11 is negative 12. F of 14 is going to be negative 11, I think. No, what am I saying? What about the 2 times? What is 2 times 12? 24? Negative 24 plus 1 is negative 23. My bad. And then 2 times negative 23 is negative 46 plus 1 gives us negative 45. The answer to this is going to be letter choice B, right? Negative 45. All right, this one is a little bit weird. And you might have to read this a few times. It's another recursive function problem, but we are not going to approach it the same way we solve other recursive functions. Let's take a look at this. It says define Fasano's function as p of n is equal to 0 when 0 when n is equal to 1, 1 if n is equal to 2, and then for every other term where n is greater than or equal to 3, we have p of n minus 1 plus p of n minus 2 mod m. It defines the Pisano period as the number of terms that repeat, and then it gives an example. So for mod 2, the sequence becomes 0, 1, 1, 0, 1, 1. So the Pisano period for mod 2 is 3, right? Basically, it's taking into account how long the sequence of numbers that is continuously being repeated is, and that is essentially the Pisano period. Like we're basically trying to find the Pisano period. Now, there's two variables to keep in mind here. The first one is n, which basically just acts as like the x in like an f of x function, right? Nothing special or new about that. There's also this mod m thing. If you guys haven't figured that out already, this basically just means modulus some number, right? The only thing that they're basically saying that for every single like number where we're changing the value of m, we're changing the modulus that we're changing the modulus by, our Pisano period is going to change. In this case, they ask what is the Pisano period for mod 4, so let's just write that here. Let's define that. And once again, we are not approaching this the same way as we are approaching other recursive function problems, right? Other recursive function problems, they tell us, oh, okay, well, here's your recursive function. I want you to find like f of 16 or something, right? We don't really have like a starting place in this case. We're not looking for something specific. We essentially just need to generate a series of numbers that make up a sequence until we see that repeating pattern. When we do see that repeating pattern, then we know that we have our Pisano period. So we're literally just going to start at n equals 1. At n equals 1, our value is going to be 0, and we know that because they say that. At n equals 2, our number is going to be 1. For every term that follows, we're going to take the sum of the previous two numbers. So in the case of 3, it'll be when n equals 1 and n equals 2. And we're going to take the sum of those two numbers, and then we're going to modulus it by 4. So 0 plus 1 is 1. 1 mod 4 is just going to be another 1. And this kind of just repeats, right? It's kind of like a Fibonacci sequence. So let's keep going. 1 plus 1, that gives us 2. 2 modulus 4 gives us 2. 1 plus 2, that gives us a sum of 3. 3 modulus 4 is 3. 2 plus 3, that gives us a sum of 5. 5 mod 4 gives us 1. 3 plus 1, 4. 4 modulus 4 is 0. 1 plus 0, 1. 1 modulus 4 is 1. 0 plus 1, sum is 1. 1 modulus 4 is 1. 1 plus 2, 2. 2 modulus 4 is 2. 1 plus 2 is 3. 3 modulus 4 is 3. 2 plus 3 is 5. 5 modulus 4 is 1. And then it just keeps going on and on and on. At this point in time, we've already actually begun to see a pattern here. So the pattern is going to be 0, 1, 1, 2, 3, 1. After that, it repeats again, 0, 1, 1, 2, 3, 1. And then if we were to keep going, the next number in the sequence would be 0, right? 3 plus 1 is 4. 4 modulus 4 is 0. So now that we have our sequence of repeating different digits, all we need to see is how many digits there are in said sequence. So in this case, there's going to be 6 digits in the specific order of 0, 1, 1, 2, 3, 1, which gives us a Pisano period of 6. The answer to this is going to be B. This is not a hard problem to solve per se. It's more just, can you read and comprehend what they're exactly asking you to do? Do not get so caught up in the fact that most recursive function problems look like this, right? If you see something like this where it's a little bit different, don't freak out. Just read it carefully and it'll become doable. All right, number 7. Digital electronics. It's a simple simplification problem to simplify the Boolean expression represented by the circuit. All right, let's do this. So we have A times B with an extended not bar over it. This can be broken down via De Morgan's law to not A plus not B. This one, on the other hand, is going to be B plus C. And extended not bar on top. This, again, can also be broken down using De Morgan's law into not B times not C. I'm going to erase these. These two are going to be brought together by an and. So I'm actually going to just immediately write it like this, so you guys can see the multiplication that I'm doing, right? But this is going to become not A times not B times not C plus not B times not C, right? When we have something like this, we have a not B not C here, we have a not B not C here. That's going to cancel out. This entire thing will just simplify to not B times not C. Just to keep it organized. And then finally, we have a not B times not C plus regular C. I think this can be simplified. I'm not actually sure. I mean, it doesn't really need to be because that's one of the other choices, but Let me see. Yeah, this could technically be simplified further using number lon or what is it? What are these called? Identity number 11. And this, oh wait, can it? Yeah, I think this could technically become not B plus not C. But we don't need to go that far because answer choice A already gives us what we want. So the answer to number 7 is going to be A. Simple. All right, this one. What single gate can be placed in the digital diagram to replace the rectangle so that the least number of ordered triples would make the following circuit true? Okay, this one is a little tricky, but we're gonna get through it. So the first one is an XOR gate. So this is going to be this is going to give us a. I'm not actually even gonna bother simplifying this out. A XOR B, and then this one is B plus C, and not bar over top. Gonna simplify to not B, not C. Get rid of this. And it's asking us what gate and or not or I don't really understand this none of the above. I guess I can or expression, I suppose, but let's not really worry about this for now. Out of these four, I guess okay, wait, actually now that I'm thinking about it, I suppose there could be other gates, like another XOR or like a not XOR or something like that. That are you asking if that's the answer? Yeah, I'm still going over it. Okay, but yes, I'll go over it. But like, yes, that is the answer, I think. Okay, yeah. Anyways, the way that you can approach this is you can plug in each one of these four, I suppose, and just continue simplifying it. That is one valid way of doing it, but that's gonna take a bit of time. Another way we can do it is to figure out what order, well, another way we can do it is to figure out exactly what order triplets are allowed for each of these two conditions. So for the XOR, right? Remember that these are triplets. There is a C. So for the first one, this is going to return true for anytime A and B are opposing values, right? So when A is 0 and B is 1, and then when A is 1 and B is 0. Right? So for the first one, there's a total of 4 ordered triplets where it's true. For not B, not C, this is going to return true as long as both B and C are false. So that gives us 0, 0, 0, and 0, 0, 1. Again, to make this order triplet true, right? So far we have like true, true. In the instance of an AND gate will only return true when an ordered triplet is found in both A, X, or B and not B, not C, right? Oh, wait, I wrote this wrong. Sorry. Sorry, A is the one that changes. I was like, this looks funny. Okay, sorry. The AND operator is only going to return true as long as an ordered triplet is in both of these, right? An ordered triplet, the AND gate requires both of the inputs to be true, and these are all of the ordered triplets that will return true for each of these two branches. There is one instance where we have a repeating order triplet between the two of them, and that is going to be the 1, 0, 0 order triplet. So only one of the two is going to give a true value if we implement an AND gate, right? What about the OR? How does an OR work? Well, an OR gate is going to return true as long as any one of these 5 order triplets gives us true, right? Because there's actually 5. I know there's looks like there's 6, but 1, 0, 0 is the repeating one between the two of them. right? The OR operator only requires like one true test case to be found, one triple that'll return a true anywhere, whether it's in like that top branch, that first input, or whether it's in the second input. It literally does not matter. So as long as we have any one of these five, it's good to go. So the OR operator again has five. Now the not and the not or, that's just the and or the or, and then it's like reverse, right? So if we have a total of 8 triples that are available for us to use, and only one of them gives us a true value from and, that means 7 of them is going to give us a true value if we use not and. Same logic for the or. If 5 of the ordered triples gives us a true value for the or, then 3 of them are going to give us a 3 of us. Okay, hold on. 3 of them are going to give us a true value for not or. We can, I guess we can check XOR hypothetically. I didn't even think about what XOR would give us. XOR is going to be, we need to have something that'll give us a true value in one and a false value in the other. So that's going to be an ordered triplet that's found in one but not the other, right? So that's going to be 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, or 0, 0, 0, right? So 1, 2, 3, 4. That means XOR is going to give us 4 true values, and then not XOR is also going to give us 4 true values. Now, the question asks us, what single gate can be placed to replace the rectangle so that the least number of ordered triples make the circuit true? Between 1, 5, 7, 3, 4, and 4, 1 is the smallest number between the 6 of them, and therefore the answer to this is going to be A for and. Sorry, give me 2 seconds. All right. All right, the last, what is it? Number 6, number 8, they're a little bit fun. We're going to go back to boring questions from that one. Number 9, evaluate the following prefix expressions. The simple evaluation one. Numbers are symbol digits. Prefix expression, we have the order operator, operand, operand. So we have plus 2, 8. We have divide 9, 3. We have exponent 2, 4. This gives us 10, 3, and 16. Then we have plus 3, 4 here. We also have a divide 10, 5. This gives us 2. This gives us 7 times 3, 7 here. I know I'm technically going out of order, right? When you guys are doing this, please do this from left to right. But anyway, we have times 3, 3, 7 gives us 21. We have minus 221 gives us negative 19. And then plus negative 19, 6 gives us a final answer of negative 3, right? It's a very, very standard, very simple evaluation problem. And so that is also going to be A. All right, number 10, change the following postfix expression to prefix. Okay, I feel like for those of you guys that I've taught ACSL to, I kind of tell you to first convert it to infix first. There's like a quick shortcut, I suppose. I don't know what other teachers necessarily say. There's like a quick shortcut, I suppose you can use, where we're not really going to be converting it into infix. We're kind of just going to convert it directly. The idea is still the same though. So let's do number 10. We're going to treat this like an evaluation problem where in the sense that we're going to be looking for those initial postfix patterns of operand, operand, operator. And then instead of exactly evaluating, we're just going to be translating them to prefix as we go along. So again, doing that boxing thing, I have 2, 3 multiplication. I have, what else do I have? 3, 2 multiplication. I have 2, 4 exponent. And then I think that's it for the first round. So for every single one of these I've boxed, instead of actually doing the math, we're just going to convert it into prefix. So this is going to become multiplication 2, 3. This is going to become multiplication 3, 2. Make sure you guys are keeping the order of the digits the same. And this is going to be exponent 2, 4. Okay, and then we're just going to keep going. We're going to assume that every single one that I've written down already as like a solved prefix conversion, that's just going to be treated as a new operand, right? So I'm going to look for postfix patterns again. So we have one right here. We have, sorry, give me, okay. We also have this one here. My line's so very messy today. And then we have another one here. Oh, I just completely missed there. Okay. Again, treat the Burgundy as a single operand, like a single number. So this is going to become times, that's the operator, times 2, 3, 4. This is going to become exponent times 3, 2, 2. This one is going to become plus exponent 2, 4. And we're going to keep going. We have a division by 6. We have a division here. We have division times 2, 3, 4, 6. And then, you know what, I'm just, I literally cannot be bothered to write all this. Okay. And then we have what is the operator? Division. Division exponent times 3, 2, 2. And we have a plus exponent 2, 4, 2. Yes, something like that. I don't know. And then the entire thing is going to get subtracted from each other. So that leaves us with subtraction. Division times 2, 3, 4, 6. Division exponent. I'll separate this a little easier to see. Division exponent times 3, 2, 2 plus exponent 2. And there we go. That is our entire final prefix expression. So if we were to look at this, we have subtraction times multiplication 2, 3, 4, 6, division exponent times 3, 2, 2 plus exponent 2, 4, 2. The answer to this is going to be answer choice B. There was no necessary conversion to infix. And there we go, right? We can just do it directly. Number 11, computer number systems. What is the next year in base 10? Your answer is going to be in base 10. After 2022, that the year expressed in octal will have 3 consecutive digits in increasing order. Consecutive indicates uh, consecutive is going to indicate, I believe, like numbers that are adjacent to each other. So think like 1, 2, 3, or like 3, 4, 5, things like that. And then obviously increasing means increasing number, right? So first thing we need to do is convert 2022 to its octal form. And the way that we are going to do that is using the ladder method. So we have 2022 divided by 8. If I am doing my division wrong, please catch it and let me know. This is going to give us a quotient of like what, 2, 5, 2 with a remainder of 6. You know what? I don't check myself. No, never mind. I'm the goat. All right. 252 divided by 8 is going to be 3, 1 with a remainder of 4. Yes. And then 31 divided by 8 is going to be 3 with a remainder of 7. Circle this one. We go backwards. Our octal number is going to be 3, 7, 4, 6. Now, we need to find the next biggest octal number, so the smallest possible octal number, where we have an increasing, like, consecutive digital pattern here. So our consecutiveness can occur in one of two places. The first place that it can occur is obviously in the first 3 digits of this number, and the second place it can occur is in the last 3 digits because it's the only places we have one of 3 digits. For 746, this is not possible to have an increasing consecutive like pattern because we're already at 7 at this position here, right? Octal number system does not have the digits of 8 and 9, so we can't have something like 3, 7, 8, 9. That basically means we're going to go up to 3777, and then it's going to reset to the number 4000. Now, from here, we can have 4560. That would be example of a consecutive one. Or we can have one that makes more sense, where these three are consecutive, and it's going to showcase 4012, right? 12 digits later, we get 4012, where 012 is an increasing consecutive set of octal digits. This is exactly what they are asking for. So now once they have this, we can then convert it back into base 10. Remember that our answer should be in base 10. If you guys see this and you choose answer choice A, that would be incorrect. This is the right answer in octal, but they're not asking for it in octal. So make sure you guys are reading very carefully. Okay, to convert an octal number back into base 10, we're just going to assign each individual column or each individual digit, whatever, exponent of 8 we're supposed to multiply it by. So 8 cubed is like, I don't know, a number. It's 512. That times 4 is going to give us 2048. 0 times 64 is just 0. 1 plus 8 is 8. And then 2 times 1 is 2. So this gives us 2052. 2058. The answer to this is going to be next. Next. Okay, number 12. Evaluate and express the answer in base 10. Base 16. What am I saying? You guys need to convert all of this to base 10. You can't multiply or divide in other bases other than base 10, so I would convert this all to base 10. Now, the good news is this is actually not hard to convert to base 10. Binary to base 10, this is like 1, 2, 4, 8, 16. 16 plus 4 plus 2 gives us 22. So that's 22. A in hexadecimal, you guys should know that's 10 in base 10. 13 in octal, this times 8 times 1. This is going to be 11 in base 10. 20 is already as 20. 6 in base 8 is 6 in base 10, so that doesn't need to change. And then that squared is going to be 36. If we implement our operators, we have a multiplication, division, subtraction, and addition here. So if we were to just do this by the order of PEMDAS, we have 22 times 10 divided by 11 gives us 20. 20 minus 20 is 0, plus 36 is 36. So our number in base 10 is going to be 36. We then need to convert that into hexadecimal, so let's use our ladder system. 36 divided by 16 is going to be 2 with a remainder of 4. Stop there. Our answer is going to be 2, 4. Answer choice B. Number 13, build a binary search tree for delta variant, and it asks what is the internal path length of the tree. Again, same thing as yesterday. They also asked for internal path length yesterday. So when you're drawing your trees, keep your nodes neat and on whatever level they're supposed to be at. What else? And also brush up on the different things, different like, what is it? Things that can ask about in terms of binary tree, internal, external path length, and then traversal path, I think was the other one. Okay, anyway, sorry, I'm getting ahead of myself. Delta variant, we have D, then we have E. L is going to go to the right of E. T is going to go to the right of L. A is going to go before all of them. V is going to go to the right of T. Another A is going to go to the left of the pre-existing A. R, Q, R, S, T. R is going to go after L but before T. I is going to go H, I, J, K, L. I is going to go after E but before L. As you can see, I don't know the alphabet very well. There's a third A, so it's going to go down here. N is going to go, after L, before T, and before R, I believe. And then finally another T. T, there's a pre-existing T, but there's already a left node, so it's going to go after the R. And this is our binary tree. Now let's draw some lines. Choose this lovely, beautiful, disgusting lime green color. Remember that the depth of our tree, or like our levels, are going to start counting at 0. So this is 0, 1, 2, 3, 4, and 5. At level 0, we have 1, but that's multiplied to 0, so I'm not even going to write it. So this is 1 times 2, this is 2 times 2, 3 times 3, 4 times 2, and 5 times 2. To give us sums of 2 plus 4 plus 9 plus 8 plus 10. That's 6, 15, 23, and 33. This is going to have an internal path length of 33. Next, number 14. Given an initially empty stack and the following commands on the stack red left and right first, what item will be popped next? Remember whenever we're building either a stack or a queue, it doesn't really matter. The only difference is you guys need to understand where we're going to be popping from, right? When we push a number, it's kind of the same as like reading or like writing something down, where we're writing the letters in the left to right format. Now, between stacks and a queue, right, whenever we're popping, it's like we're erasing letters. But the question is, do we erase from the left or do we erase from the right? A stack, we are going to be erasing from the right. So whatever we wrote last, we are going to erase first. You can also think of it as like a plate of pancakes, right? When you have a plate of pancakes, you stack them up one by one. Obviously, the bottom one has to be stacked first, and we go all the way to the top. And when you start eating them and getting rid of that stack of pancakes, nobody starts eating them from the bottom, right? We all start eating from the top. Or, okay, honestly, low-key, I kind of just cut through all of them, but that's not the point. Point is we're eating from the top, right? Whatever was placed last gets eaten first. Whatever has been written last or pushed last gets popped first. And then, like I said yesterday, for those of you guys that are actually efficient at Korean Q, that circle-y thingy looks like the whatever this letter is called in up. So I don't know. However you guys choose to remember it, I don't really care. There's a bunch of different ways. Just don't mix them up. Okay. Other than that, this is a very straightforward problem. So we're gonna push G, then we're gonna pop it. So it's gone. Then we're gonna push I, we're gonna push N, we're gonna push G, we're gonna pop the G. And then we're gonna pop the N. Oops. Then we're gonna push E, R, B, R. And then we're gonna pop 1, 2 times. So B and R are both gone. Then we're gonna push E, A, E, pop 5 times. So we get rid of the D, we get rid of the A, we get rid of the E, the R, and also the D. So at the end of going through all of these commands, the only letter actually left in our stack is going to be letter I. And if we were to add another x is equal to pop command, right, then we would pop the letter I. The answer to this is going to be D. Great. Number 15, given the directed graph below, how many paths of length 2 are there from vertex A? Okay, more multiplying matrices. Let's start by making the actual matrix itself. So we have A, B, C, D, and E. A can go to vertex B, C, D, and E. So it can go to everything except for itself. B can go to A and C. C can go to D. D can go to A and C. And then E can go to A and B. Right? Now, this is one where we can actually use the shortcut here. So it asks how many paths of length 2 are there from vertex A. So we don't actually care about the individual paths between A and a specific ending vertex. We only care that it starts from A, which basically means we can multiply this, full matrix along with the matrix with a shortened version. So starting from A of path length 1, there's 4 paths of length 1 that stem from A. There's 2 paths of length 2 that stem from B, 1 from C, 2 from D, and 2 from E. From there, we can just multiply rows and columns where we have rows from the big matrix because we only have a column to deal with here. Keep in mind, this is length 1, this is also length 1, so we want to length 2, 1. So row 0, 1, 1, 1, 1, multiplied with column 4, 2, 1, 2, 2. That's going to be 0 times 4 plus 1 times 2 plus 1 times 1 plus 1 times 2 plus 1 times 2 to give us a total sum of 7. You guys can actually keep going if you would like, but there's no points because it asks how many paths of length 2 are there from vertex A. This very first number represents the number of paths length 2 that stem from vertex A. We don't care about the rest of them. So the answer choice of this is simply going to be very standard matrix multiplication problem. Let's do number 16 next. How many cycles are from A in this directed graph? Oh my lord. Okay. Same thing. We have, let's write out like where each vertex can go. We have A, B, C, D. In fact, there's 6 vertices this time. Okay. A can go to B, D, and F. Sorry, I'm just gonna be very slow and careful with this class. Like yesterday, I messed up. B can go to A and B. C can go to A, I think just A. D can go to C. E can go to A and F. F can go to E. Okay, and then cycles, right? We start with A. We just branch out until we either reach a dead end or we find a cycle. A can go to B, D, and E. B can go to A and D. So A is the end of the cycle. Use a new branch. D can go to C. E can go to A and F. Okay. D can go to C. C can go to A. F can go to E. This is a repeat. This is a dead end. No, I missed something. I'm missing something. Oh wait, not bad. I misread my own handwriting. It's an F. Okay, let's ignore this branch for now. We'll do it later. This one can go to A, right? So out of these other 2 branches that originally stem from A, we have 1, 2, 3 cycles so far. F can go to E. E can go to A and F. 1, 2, 3. Something's not right. Where's the other ones go to? Can F also go somewhere else? Oh, it can. Bruh. Okay, moral of the story. Read very, very carefully. Sorry, F can go to D and E. Okay, that makes more sense. Bruh, I missed 2 things there. Okay, F can go to D, F can go to A. Right? No. Oh my gosh. Crap. F can go to D and E. My bad. My bad. Okay, now we're back on track. So E can go to A. It can also go to F, but this is a repeat, so we're gonna stop here. This D can go to C, and that C can also go back to A. We're done. Every single branch here has either found its way back to A or has been updated. So how many cycles are there? We have 1, 2, 3, 4, and 5. The answer to this is going to be B. Great. I feel like we're getting faster and faster. Number 17, what does this program do? This is another example of one of these questions where you guys really shouldn't be doing all this. There's a nested for loop here, the first one that goes from 1 to 10, and then the second one going from 0 to 12. That's like 130 different loop iterations, right? You're not expected to do all that. In fact, it's quite stupid. And yeah. So in that case, we need to figure out exactly what it's asking. It says, give the array fib that is filled with the Fibonacci numbers 1, 2, 3, 5, 8, 13, 21, 55, 89, 144, 233, 377, and 610 in location 0 to 12. How many numbers will be output in the following program? They're giving us an array called fib, and it has 10, no, sorry. 8, 9, 10. There's 13 numbers in our array. Our array is size 13, numbered from 0 to 12. we are looping through that using our inner for loop. We have for y is equal to 0 to 12, right? That pretty much basically tells us, oh, and also if you look at the if statement condition, right? It says fib of index position y. That basically tells us what the inner for loop is doing, right? We're traversing through the Fibonacci number sequence array. Now, the top one, or the outer for loop, is just x being filtered through 1 through 10. Not entirely sure what that is used for yet. Okay, let's take a look at our if statement condition. We have if stop is equal to 0, which is always going to be true at least once, right? Because stop is a variable that is created newly every single inner outer loop variation, outer loop integration, I guess. And then if stop is equal to 0 and Fibonacci array at index position y modulus x is equal to 0, then we're going to output x, and stop will be set to 1. Then we're going to end our if statement. Okay, this is stop variable. It's not really being used as integer. If anything, it's kind of being used like a Boolean variable almost. Um, where once we find this condition, right, our stop condition is always going to return true up until the second condition returns true. Right? We're always going to start by going into this if statement. So once we hit a sequence where our Fibonacci number is divisible by, oh sorry, where our x number is a factor, where our x number, whether it's 1 2 3 4 5 6 7 8 9 or 10, as long as it is a factor of any of these Fibonacci numbers, we're going to output that x variable, whether again it's 1 through 10, and we are also going to set stop equal to 1. Stop is never going to stop being 1, so once we find it, we're just done. It's going to keep looping, but we're never going to have a true if statement, at least for that same value of x. So it's basically checking to see all of the numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For all of these 10 numbers, as long as the number is a factor in any one of these 13 Fibonacci numbers, then we're going to output that number x. That's all it's doing. So let's go through them. One is obviously a factor of every single one of these. One is a factor of everything. So it'll be output. I'll put a check mark for if it's output. Two, if the number is even, then it'll be a factor. So yes. Three, you have a 3 in there, so yes. 4, factor of 8. 5, factor of 55. 6 is a factor of, I think 144 might be one. Yes. 6 is a factor of 144. 7 is a factor of, I don't know, 89? No. 377? No. Oh, 21. I didn't even have to look that far. 8 is a factor of 8. 9 is a factor of one of these. Is 9 a factor of me? It's not 89. Probably not 144. Oh, no, it is. What am I saying? 9 is a factor of 144, and then 10 is a factor of 610, right? So all 10 of these numbers are factors of any one of the 13 numbers in our Fibonacci number sequence, which means after we finish going through this entire program, all 10 of these numbers are going to be outputted. The question asks how many numbers will be output, not even which numbers, it just asks how many, and the answer is going to be 10. All right, last 3 questions. Again, if you guys are in the junior division, you do not need to stay. You are free to leave. The rest of you are not so lucky. After the following list program is run, what is the value of the last expression? I'm actually going to rewrite this. Or I guess retype this because it's a little easier for me. Okay. So this is our M set or our list or whatever. I'm going to underline. We have our first element. This is going to be our second element. And then this is going to be our third element. We have a function of CADDR, so we're going to do a CDR first, then another CDR, and then finally a CAR to finish off. When we do a CDR, okay, let's start with the CDR. The CDR, we take out every element except for the first, and then we wrap another pair of parentheses around it. So element number 2 is B, CAD. Element number 3, uh, element number 3 is AB, EB, like that. And then these are going to have parentheses. If we were to underline again, we have ECAD, AAB. Let's do another TDR. Another TDR is going to give us everything again, everything except for that first element. That's just going to be AB, E. There we go. We underline again. And then CAR is going to take out the first element, and we are not going to place in the parentheses over the top or on top of that, or around it, whatever you want to call it. So then we are essentially just left with this. Parentheses, parentheses, A, B, closing parentheses, opening parentheses, B, closing parentheses, B, closing parentheses. That is going to be answer choice A. This one, simpler, quicker than other list problems, I suppose. Number 19, FSAs. Welcome to the ACSL grocery store. Today, items are on sale if they satisfy the following regular expressions. So the first chunk, we need to have one letter, at least, not at least, sorry, just we need to have one letter, or it needs to start with a letter that is not A, B, I, O, or U. Let's actually just go through and like eliminate everything that's such. So bread without, dang, that was the only one. Unlucky. Okay. The second letter has to be H, R, or O. So that eliminates fish, that eliminates meat. Pickles, coffee is fine, cream is fine, chocolate is fine, cookies is fine, chips is fine, and grapes is also fine. Next, we're gonna stop looking at the first two. I'm gonna cross them out with a different color. For the rest of this, the rest of the word, we're going to stop looking at the first two letters because they have an asterisk, which basically means, like I said yesterday, it basically states that you could have zero instances, you could have one, or like as many instances as you want of whatever that letter is going to be or whatever that character is going to be. That's why there's kind of a lot of variability. So if we look at EESE, this one works, right? This is fine. E and E are, sorry, E falls within the category of A through J. So we could say that the first two E's are from here. The second one says we can have an unlimited number of letters as long as the letters are either E or S. So that works for the last two as well, right? S and E. So it could be like 2, 2, or it could be like all four of them are part of this last condition or this last, like, whatever this is, FSA. It doesn't really matter. Point is cheese works, right? Now let's look at chip. We have I and E. I, H, I, J. I is okay. I fulfills this condition. E does not, which basically means P would have to go in here. But because P is not E or S, this one actually fails our regular expression. Let's take a look at chocolate. Chocolate immediately fails. O does not fit into either one of these two conditions. O is not within A through J, and O is not E or S, so this also fails. Cream, E and A are within the bounds of A. J, M is not, but M is not an E or an S, so this is also going to fail. Great. A falls within the boundaries of the first, P does not, but P also does not fall within the boundaries of the second, so this one's also eliminated. Cookies, that O immediately fails it. Coffee, the two F's can go in the A through J. The two E's can also actually go in the A through J. Or the two E's can go in the E or the S condition. So coffee works. And then crackers, A, C, H, I, J, K. A and C can go in the first initial category. K cannot because it comes after J in the alphabet, and K is also not an E or an S, so this condition will also fail. We are left with cheese and coffee as our two items that satisfy our regular expression. How many items is that? That's going to be two items. The answer is going to be the letter B. All right, last question, assembly language. What is printed when the program is run if the data is 8 and 5? Now, there is absolutely nothing new about this. You guys know how to do this. The only thing that is a little unfamiliar from, we'll say, like yesterday's assembly language problem is that instead of just giving you the variable value, for example, like TDC0, right? That's a variable T that is declared to have the value of 0. We instead have these read variables where the variable name is on the right-hand side instead of on the left. But it doesn't matter. Inputs are going to always be in the order that they give you. So if it says read N3, that basically is saying we're reading from an outside source. And again, we're going in order. So N3, the variable N3 is going to have the value of 8. A variable N2 is going to have the value of 5. Other than that, this is exactly the same. So let's set up our variables here. We have P and 3 and then 2. For now, I think we will also have an N1 eventually. And on the right-hand side is where I'm going to be doing the actual like loading stuff. So P is going to be originally 0. I'm sorry, and N1. P is originally 0, N3 is originally 8, and N2 is originally 5. We're going to start by loading in N3. We're going to subtract N2 from that. And we're going to store that in N1. And we're going to load N3 again, multiply it by N3 to give us 64, add T, and store this in T. We're going to load N2 and store that in N3. And we're going to load N1 and store that in N2. e.g., if the value is greater, G for greater than 0, then we're going to loop way back up to the beginning where it says loop. Or we're going to start again. We're going to load N3. I'm actually going to start it in a new column because this is a loop, right? I'm assuming that there's going to be some sort of pattern that they want us to see. Yeah, let's just start over. Okay, we're going to start by loading N3, so that's 5, subtracting N2, and then we're going to store that in N1. We're going to load N3, multiply it by itself to give us 25, and then add T to that. That's going to give us what, 89? Okay, this pattern is stupid. Whatever. Is it 89? Where am I? Add T. Yeah, it's 89. We're going to then store that in T. Then we're going to load N2, store that in N3, load N1, and store this in N2. It's still greater than 0, so we're going to go back up to loop. We load N3, we load N3, we're going to subtract N2, store this in N1, we're going to load N3, multiply it by itself, and add T to it. So this is going to give us 98. That's going to give us 98. We're going to store that in T. We're going to then load N2, store it in N3, wait, load N2, store it in N3. Yeah, sorry. Store it in N3. We're going to load N1 and store this in N2. It's still greater than 0. I assume by the way that things are going that the next loop is going to be our last. We're going to go back up to the top. We're going to load N3, subtract N2, store this in N1, load n3, multiply it to itself, add c1, add c to give us 102. Then we're going to store that in t. And we're going to load n2. We're going to store this in n3. We're going to load n1. Store this in n2. Bruh. Darn, that was not the end. Okay, we do it again. Let's do it again. We're going to load n3. We're going to subtract n2. Sorry, n2 is 0 right now. We're going to subtract n2. That gives us 1. We're going to store that in n1. We're going to load n3, multiply by itself to get 1 again. We add t to that, get 1 out of 3. We're going to store that in t. Then we're going to load n2, store it in n3. We're going to load n1. Wait, what? Store it in n3. I didn't mess up, did I? Isn't this supposed to be 0? When did I last store something? No, I don't think so. Okay. Wait, where was I? I got lost. I'm just gonna backtrack to whatever I was at. Okay, whatever. Sorry. Let's add this to T. Store this in T. Load N2. Store this in N3. Load N1. Store it in N2. I 100% messed something up. What the? Hold on. Give me a second. Did I mess up? 25. 9. 1. I think I did mess up. The loop should have ended by now. Oh, wait, this is actually such a pain. I freaking hate this. Okay, I'm not gonna lie. Did I mess up? Okay, I have a feeling that this loop was supposed to end by now, which is the only reason I'm hesitant to keep going. You know what? Let's say for the sake of finishing it. Okay, I did not. So in that case, I'm just gonna keep going. If it like doesn't end by the next one, then I 100%. But whatever, keep going. Two, start this in N3, load N1, store this in N2, PG loop again, load N3, subtract N2 to give us -1, store this in N1, load N3, multiply it by itself, add to T to give us 103, store this in T, load N2, store that in N3, load N1, store it in N2. Oh, wait, maybe I didn't mess up. Maybe we're chilling. And then, okay, now our value is negative, right? It's below, wait, yeah. Now our value is no longer greater than 0, so we're not going to go to loop. We're finally done and free. We're going to load t, which is 103, add 1 to give us 104, store this in t, and then finally print. The answer to this is C. Okay, my bad. That was messy and disgusting, and I hate assembly language, but whatever. All right. The reason why I was so hesitant to keep on going and the reason why I thought I made a mistake is because there actually is a pattern to this. And if you guys notice the pattern, then you wouldn't technically have had to suffer and put yourself through this like I just did. The pattern is this is adding up the numbers of the Fibonacci sequence squared, like where each digit is squared, and we're summing up all of those squared values, right? So 8 and 5, you'll notice that N3, N2, and N1, these are all like snippets of the Fibonacci sequence. It's the exact same snippet. It's just like, and we're essentially like shifting our window when we're viewing at our Fibonacci sequence downwards, like backwards by, one placement every single time, right? So for N3, that one went the furthest because it started at 8. 8, 5, 3, 2, 1, 0. At the end, it gets kind of weird, but it doesn't really matter because we have the Beachy condition here, right? The Beachy condition essentially makes it so our addition stops once we reach, well, a value of 0 or even a negative number in our Fibonacci sequence. Same thing with N2, right? It's the same thing as N3. It's just shifted down by a factor of 1. So we have 5, 3, 2, 1, 0, 1, blah, 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 blah. And then N1 is shifted 1 down even further than N2, where it kind of just looks like this, right? All of that is like whatever. If you saw that you maybe, hopefully, it's a little hard to see if we just start at 8, but maybe you guys were able to be like, okay, wait, this is just a Fibonacci sequence backwards starting from 8, right? And then T was where we were multiplying N3 by itself to square it, and we were just basically cumulatively adding all of those stuff together. So that took us from 0 to 64, plus 25 give us 89, plus 9 to give us 98, 102, and then finally 103, right? So basically, we have our Fibonacci sequence 0, 1, 1, 2, 3, 5, 8. All right. Where if we square all of these, well, this is just going to give a 0. 0, 1, 1, 4, 9, 25, 64. If we were to add up all of these numbers, right, this would give us 104 because that's exactly what happened here. That's the purpose of this assembly language program, right? The only thing that is a little bit iffy here is this pattern isn't really inherently obvious to see, especially as it gets towards the end, which is why it was tripping me up a little bit. But that's also why they do have this like random add plus 1 here. That's to offset the fact that there are 2 1s here, right? In either case, it doesn't really matter whether you guys, observe the Fibonacci sequence and, just solved it by squaring and summing like this, or you went through the entirety of the assembly language. If you did it correctly, right, your answer should have come out to become the BC, which is 104. I will say, even if you guys did recognize the pattern, you guys should probably just use it as like a fact checker and like just to make sure that you are ending up with the right answer. Because if it like makes sense here and it matches whatever you got at the end of your program run through, then you probably did this correctly and you were like good to go, right? Um, and and then obviously the offside is you don't recognize the pattern at all and you just run through the entirety of the assembly language program, in which case that's fine too. Because assuming you did it correctly, you should still end up with the right answer, which is 104. All right. Any questions about this? I believe that is it. Yes, no, maybe so. All right, we actually got through this way faster than we did the other ones, which I'm a little surprised about, but whatever. All right, we have 10 minutes left. I can either let you guys free. In fact, that's actually exactly what I'm going to be doing. If you guys don't have any more questions for me, that's pretty much all I am going over today. Please make sure you guys do whatever homework channel team assigns for you. I think tomorrow the schedule is, I have no idea what the schedule is. It says like homework review or something. I'll ask her again. Oh, if Joel, you're here, I totally forgot to ask the thing. I'll ask it right now before I forget. My brain is in shambles. My bad.
Are you okay?
Me?
Yeah.
Oh, is on my keyboard? Yes, my bad. Okay, sorry. I totally forgot that one of you asked me to ask the question to Kyung's name and I forgot. So I just I just asked her right now. Anyways, what was I saying? Yeah, I'm assuming that I'm like going over whatever questions you guys had on your assigned homework for the past like 3 days. So yeah, please make sure you guys are doing past 2, 3 days. Please make sure you guys are doing your homework, and if you have questions, come prepared with those questions. If nobody gives me questions, I'm gonna just pick and choose random concepts that I think you guys are struggling with. And I guess we'll go from there. Anyway, that's the plan for tomorrow. I believe that is also at 7 p.m. Other than that, I don't have anything else for you guys, at least for today. Feel free to stay and ask me questions if you have any. Otherwise, you guys are free to go, and I'll see you tomorrow.
Thank you.
Thank
Bye-bye.
you.
Bye.